So today I would like first to finish what I started yesterday, namely the distribution of points on the product of P1 by P1. So maybe let me recall what yesterday at the end I was a little bit too fast, so let me start with using, so we are looking at P1 times P1, and as I said yesterday, it's possible to define a height given by the height of P at the power m times the height of Q at the power n. And I was assuming that m is strictly bigger than n. Okay, so to describe the distribution, let U in P1 times P1 of a k, so in the adelic points of the product, be an open subset of the following form. So I take it to be a product of two, in fact, elementary sets elementary open subsets in the adelic points of the projective line. So in that case, I proved yesterday that on P1 we can describe the number of points which are in each of these subsets. So okay, so now we are interested in the following cardinal. So the cardinal of the set of points PQ in P1 times P1 of Q, such that, well, they belong to this particular open subset U, and the height of PQ is less than B. And as I wrote yesterday, you can write it as a sum for P in P1 of Q intersected with U1 of the cardinal of the Q in P1 of Q intersected with U2, such that the height of P is less than the height of Q, is less than B over the height of P at the power m, and I put everything at the power 1 over n. And I want to estimate this sum. So let me summarize the facts we know. So the first thing is that yesterday we described the measure for the distribution of points on P1. So there is a measure omega on P1 of AK, such that if I look at the cardinal of the points such that so in P1 of Q intersected with U2, such that the height of P is less than, let's say, B prime, then this is equivalent, as B prime goes to infinity, to 2 over zeta q of 2 times omega of u2 times B prime square. Okay, so omega was a probability measure, so I have to multiply it by the constant we obtained, which was 2 over zeta q of 2, which is a constant which appears for the projective space of dimension 1. So that's the first fact. The second fact we know is that if I look at this cardinal, such that the height of P is less than B prime, well, it's easily seen to be less than some constant times B prime square. And the reason for this is that if I look at that, it is equal to 0 if B prime is less than 1. Okay, so that's an easy upper bound for this cardinal. And the last thing I shall use is that if I look at the height zeta function for P1 on H, then the sum for 2, so m over n, is convergent. And this is exactly the sum for P belonging to P1 of Q of 1 over H of P at the power 2m over n. Okay, that's it. So the reason for that, as I said yesterday, is because, well, 2m over n is strictly bigger than 1. So now I want to use all these facts we have seen yesterday to prove an estimate for this sum. So I do it quite, well, I'm not looking for a precise error term, so I will forget about that, and I do it in a, well, how to say, lazy way. So first of all, well, let's take some epsilon strictly positive. Well, take some I subset in P1 of Q to be finite, such that the sum for P not in I, P in P2, P1 of Q, of 1 over H of P at the power 2m over n is less than, well, let's say epsilon divided by 2 multiplied by, what do I need? Something like C, yes, plus 2 over zeta q of 2. Okay. So I may assume that since the sum is convergent. Okay. And then for any, choose some B naught in R such that for any P belonging to I, so we can do that since I is a finite set, we have that. So I'm using the equivalence here. So the cardinal of the P in P1 of Q intersected with U2 such that the height of P is less than b prime minus, well, the other term, 2 over zeta q of 2 times omega of u2 times b prime square. This is less than, so what do I need? This is less than epsilon over the cardinal of I times b prime if b prime square, sorry. If, so what do I need? If, let's say, sorry, b prime is bigger than b naught divided by h of p at the power m. I put a square here and I take 1 over n. Did I forget something? Yeah, I remove the square. Okay, so b prime will be b over h of p power m at the power 1 over n. That's the reason for which I'm doing that. Okay, so since the set of p I'm using is finite, it's okay to take something like that, this condition. Okay, so now if I have split the epsilons in the right way, so otherwise it's an exercise to correct the epsilons, then what I get that if b is bigger than b0, then, well, the cardinal, the sum over there, so the cardinal of the PQ in P1 cross P1 of Q intersected with U such that the height for M on N of PQ is less than B minus the sum, so there is something like 2 times zeta q of 2 and the sum, I'm forgetting something, yeah, omega of u2, the sum for p in p1, okay, I should write it on the next line because otherwise you won't be able to read it. So minus 2 over zeta q of 2, omega of u2. The sum for p in p1 of q intersected with u1 of 1 over h of p at the power 2 times m over n times b square is less than epsilon times b square. So the error terms, well, I have to split it in 2 parts, which are the part corresponding to p belonging to I and the part corresponding to p not belonging to I. For the part not belonging to I have this upper bound which gives epsilon over 2, and here I forgot the terms 2, and for the part for p in I have this upper bound which should give another epsilon over 2. So this gives epsilon times b square. So we get that this is equivalent to this as b goes to infinity. So the asymptotic distribution is given by Well, the volume, well, for M on N of some open subset U should be something like that. So it will be the sum for P belonging to P1 of Q of the measure for P1, let's write it P1, of the fiber over P intersected with U times 1 over H of P at the power 2 M over N divided. So I have to make a probability measure out of that. So I divide it by zeta P1 of 2 M over N, which corresponds to the sum of these coefficients. So, okay, so I multiply each probability measure by this coefficient. So if I take U to be the whole adelic space, here I get 1, here I get the sum over 1, the sum of the 1 over H of P at the power 2 M over N, and I divide by exactly this, so I get a probability measure. Okay, so you see, it's a measure which is supported or rather the support of which is the union for P belonging to P1 of Q of the fiber over P. So it's far from being a continuous measure. If we had a continuous measure, removing one of the fiber would not change the measure because it's continuous, and for a continuous measure relative to, let's say, Lebesgue measure, removing one line would not change anything. So it's far from being a continuous measure. And in fact, if I had drawn a picture to show you on a computer, the picture you get is more or less like that. Well, okay, you have your projection to P1, and you are looking at the fibers over this projection. So let me draw P1. So you see here I'm dividing by the height of P at some power. So if I take here a point P, let's say, for example, 0, 1, with small height, then this means, when you look at that, that in the fiber, there will be a lot of points. So here, you get a lot of points in the fibers. On the other hand, so there are a few such lines with small heights. Let's say, for example, 1, 1, or minus 1, let's say 1, minus 1, okay, which has the same height as 0, 1, and 1, 1. But as soon as you look at points with bigger height, then the coefficient here you get here is smaller, and it is quickly very small, since in fact the sum is converging. So after that, you get vertical lines, fibers, with less points. And very quickly, you have very few points. So when you draw the picture, and I have not the picture with me today, but if I will try to show it to you tomorrow, if you look at the picture, you see the vertical lines. And you see the vertical lines corresponding to the points with the lowest height. It's very clear on the picture. So maybe I will try tomorrow to bring a sequence of pictures so you can see this phenomenon. Okay, so that's it. So, of course, if I exchange m on n, well, everything is symmetric, so you get the same thing, but with horizontal lines. So, the remaining case, and somehow the most interesting, is a case where m is equal to n. So let me now go to the case m equals to n. So in order to do that, I will use a two parameters zeta function, namely I use zeta of P1 cross P1 of, let's say, R on S to be the sum for PQ in P1 cross P1 of Q of 1 over h of P at the power R times h of Q at the power S, which I may write very easily as zeta of P1, the height zeta function for P1 of R, times the height zeta function for P1 of S. Well, so what can I say? Well, the point is that the height zeta function corresponding to any m on n can be expressed in terms of this one by reducing to a line. So in fact, if I want to look, so this is a trivial remark. If I want to look at the height zeta function corresponding to the height hmn, so this is in one variable s, then this is simply given by looking at this expression of the zeta function. So I look at the zeta function in two variables at ms and ns. So in particular, it's easy to get from this expression the domain of convergence of the height zeta functions, namely, well, this height zeta function converges, well, if the real part of S is bigger than the maximum of 1 over m 1 over n. Is that correct? Yes? No? It's 2 over m. 2 over n. So, okay, here the point is that the height zeta function for P1 converges for the coefficient bigger, the real part of the coefficient bigger than 2. So I get 2 over m, 2 over n. Well, it has a pole in max of 2 over m, 2 over n of order 1 if m is different from n, and of order 2 if m is equal to n. So we get already, using Tauberian techniques as I explained yesterday, that in fact, for m equal to n, we get that the number of points in Pn cross Pn of height for HMM of b of height less than b is equivalent, as b goes to infinity, to some constant which is in fact 2 over zeta q of 2 square times times b at the power well, it will be 2 over m times the logarithm of b at the power 2 over m. So this is given by the Tauberian results I quickly described yesterday. Okay, but in fact, I can push this a little bit further. Namely, instead of looking at the zeta function of the wall of P1 cross P1, I can look at the corresponding zeta function, but this time for points in some open subset. So again, I take U to be an open subset in the adelic space as before. By this I mean that U1 and U2 are elementary. And I can look at the zeta function of U for H M M of S to be, well, the sum for PQ belonging to P1 cross P1 of Q intersected with U of 1 over the height of P at the power S. Well, again, the result is quite similar to the one we had before. Namely, it will be zeta of U1 for the usual height of MS times zeta of U2 H of MS. And again, we know what happens for this height zeta function. Namely, well, this converges for real part of S bigger than 2 over M. And it has, well, I assume it, well, I should assume U to be different from the empty set. And it has a pole of order 2 at S equal to 2 over M. And the limit as S goes to 2 over M of this zeta height zeta function zeta U HMM of S times S minus 2 over M square. Well, it will be something like well, let's say, let me write it as follows. It will be equal to the limit as S goes to 2 over M of zeta of P1 times P1 HMM of S times S 2 over M. So the limit for the zeta function where I do not look at the open set times what? Times omega 1 of U, omega P1 of U, 1 times omega P1 of U2. So we get from that that the measures converges to the product of the measures. So then we get that the measure is given by something which is continuous, and we get equidistribution. And in fact, in that case, if you make the drawing, you get a picture which is more or less like that. You still see the vertical lines on the horizontal lines, but you see both of them. And you see more of them. So the point is that if you think a little bit about it, the contribution of the whole, I mean the thing we obtain here is with a term which is logarithm of b. But if you look at one horizontal line, the contribution of one horizontal line will be a constant times b. So the contribution of a line is negligible, since there is a term logarithm of b here. But it is not that negligible, if you take my meaning. So in fact, you see the horizontal lines and the vertical lines. So I should make a nota bene. So some constant depending on the line times b at the power 2 over m, which is negligible when compared with this term. So maybe I didn't say the right power, but that's the point. So up to the multiplication by the logarithm. Okay. Oh, so now I think I do not want to say more about the distribution over Q. So let's turn to the distribution over K of t. So yeah, no, one last remark, which is important. I could have done exactly the same with the product of two projective spaces. So I could do the same for, let's say, PA times PB over Q. What do we get in that case? So once again, everything we have done for P1 cross P1 works exactly the same. So there is no problem. And you get the following result. Well, if so you have the height HMN, which is the height over PA at the power M times the height over PB at the power N. So if M over A plus 1 is bigger than N over B plus 1, then the measure is supported by the vertical lines, so to say. The union for P in P A of Q of the fibers over P if m over a plus 1 is less than n over b plus 1, you get a similar result, but instead with the fibers of the second projection. And if you have that these two quantities are equal, m over a plus 1 is equal to n over b plus 1, you get equidistribution. And once again, the measure is the product of the measures on each projective space. And the constant, what is the constant? Or whether the asymptotic behavior. Well, and again, you get a logarithm factor, so npa cross pm of hmn, so sorry, pb of capital B is equivalent to some constant which is a constant for PA times the constant for PB times B at the power a plus 1 over m logarithm of B at the power a plus 1 over m if m over a plus 1 is equal to n over b plus 1. Well, so in particular, you see that the power of B is equal to 1. So you have equidistribution and the power of B equals to 1 if A is equal to, M is equal to A plus 1 and N is equal to B plus 1. And what is this particular line bundle you obtain? So this means the height is given by the embedding of PA times PB into some projective space, so that the pullback of O of 1 on this projective space is equal to O of A plus 1 B plus 1, which is the opposite of the canonical line model. So, the conclusion of this first example to get equidistribution in that case, in that very particular case, we need to take an embedding associated to a multiple of the anticanonical line model. And to get a power of B which is equal to 1, you need to take really the anticanonical line model. Well, if you look at the previous example, namely PM, it's exactly the same. Because for PM, I got B at the power n plus 1. So if I take multiple of the line bundle, I mean O of n, then I will get, for the projective space of dimension m plus 1 divided by n. So again, to get a power of B which is equal to 1, I have to take the anticanonical line model. So this is the same for the projective space. Okay. So now to the geometric setting. So it should be something like before. Okay, so again, I write it for P1 cross P1, but of course you can do it for the product of any projective spaces. Well, in fact, I do it exactly for product of two projective spaces. Well, the result is quite obvious. Namely, well, of course there is a B degree there. So if you have for any morphism F from P1 to PA times PB over K, well, you have a B degree which is, well, let's say degree of F is given by the degree of the pullback of the vector bundle corresponding to the first factor, and then the degree of the second one. Therefore, we can write and consider the morphism of B degree equals to DE from P1 to PA times PB. And this scheme is very easy to describe. To give a morphism to the product is the same as giving a morphism into each term. So this is canonically isomorphic to the morphism to the first factor times the morphisms to the second factor. If you want to write it in terms of the motivic height zeta function, well, it simply says that the motivic height zeta function, so let's define it with two parameters, let's say T and U. So the sum for DE of the class of the morphism of degree DE from P1 to PA times PB T at the power D, U at the power E, well, is simply the product of the two motivic height zeta function for each term. So now the results are quite obvious to describe. So if I were to insist of using a single line bundle to measure the degree, then what do I get? If I use the degree relative to some ample line bundle to O of Mn, what do I get? Well, I get simply a disjoint union for M, Mk plus Nl equals to D of the morphism of B degree KL of going from P1 to PA times PB. Right, and this decomposition corresponds to, in fact, the connected components of this scheme. Okay, and then if I take, okay, maybe I should have written it somewhere, I forgot. So if we look at the symbol corresponding to this product, so recall that, the morphism of, let's say, degree D from P1 to PA, its symbol is given by, so L at the power D times A plus 1 times L at the power A times 1 minus L at the power minus A minus 1 times 1 minus L at the power minus A over 1 minus L minus 1. Well, if I should say if D is bigger than 1. So up to some constant, one should remember that the dimension we get is D times A plus 1, up to something which is bounded. So now if I look at that, the dimension of that, or let's say the dominant term, will be something like K L K A plus 1 plus L times B plus 1. I take the product of the two expressions I get, and I look at this. This is constant, so I look at the first term, which is the only one depending on D. Okay, so what you get is that if you want to look at the component of the highest dimension, you have to look at the term for which this expression is bigger. So the component with the biggest dimension is the one with the biggest, so K A plus 1 times, plus L B plus 1. Okay, but I have this condition. Mk plus Nl is supposed to be equal to D. So, so Mk plus Nl is equal to D, which is fixed. So now if I have that M over A plus 1 is strictly bigger than N over B plus 1, then the component of highest dimension is the one with okay, I have 1 chance over 2, either the smallest or the biggest K, so I have to check that. So, so maybe I should k prime take k prime to be mk, L prime to be NL. Then I have that k prime plus L prime is equal to D, and I have to have k prime A plus 1 over M plus L prime B plus 1 over N. So we get it for A plus 1 over M is less than for the highest L prime. So I have to take, so I can remove the prime now. I have to take k as small as possible. Okay, but then if I look at this description here, this means that in fact I take this product with k here as small as possible. But what did I say yesterday? I said yesterday that if you want to have equidistribution in a geometric science, you have to have the degree as big as possible. But here I am taking one of the degree as small as possible. So this means that at least here I won't have the equidistribution because I do not allow the k to go to infinity. So, I mean, the problem we have seen in the arithmetic setting is exactly the same in the geometric setting. We can't have equidistribution if we do not allow both of the degrees to go to infinity. So, as over Q, if M over A plus 1 is different from N over B plus 1, we can't have equidistribution. But it's worse than that. Even if I take M over A plus 1 equals to N over B plus 1. What does it mean? It means that all the components have the same dimension. So it's almost all right. I mean, because okay, so you write somehow your disjoint union. Well, you have the two extremities somehow corresponding to small k or small l, for which you don't have equidistribution. On all other components, you get better and better equidistribution. But still, you have these components at each end of the sum, for which you do not have equidistribution and which have a constant dimension. So, well, again, to really have equidistribution, you have to remove something. You really have to consider the B degree, which is not surprising when you think of it. But well, and obviously, once you have realized that, I mean, it's probably obvious for some of you, but once you have realized that, well, you have the result, which I may state as yesterday, namely, let Z in P1 of K a closed subscheme. Let Y be some subscheme subscheme of the morphism from Z to PA times PB. And let's consider the morphism of B degree D on E from P1 to PA cross PB, such that the restriction to Z belongs to Y. Let's divide this by L at the power A plus 1 times D plus B plus 1 times E. And let's multiply this by the space of morphism from Z to PA times PB. Well, then this, I can write it as a difference, minus the morphism of Y degree DE from P1 to PA times PB divided by L at the power A plus 1 D plus B plus 1 E times Y goes to 0. Well, yeah, it goes to 0 as both degree D on E goes to infinity. Actually, I should write this as okay, I take the difference between the two terms. So, okay, so this is a quick distribution. Okay, so now you should, really tell me that all this is completely obvious and that I'm spending too much time on it. Because if you think of it, the right way to see freeness is to look at the pullback of the tangent space and look at the decomposition of the pullback of the tangent space. So, of course, if you take f from P1 to PA times PB, then the pullback of the tangent space, so it's isomorphic to O of A plus 1 times D, so of P degree DE plus O of P1 of B plus 1 times E. So it's not very surprising that to have something which is really as free as you want, you need both D and E to go to infinity. Maybe the last thing I should note is that this term, as I made a remark in the arithmetic setting that in fact the right line model was corresponding to the anticanonical line model. The anticanonical line model appears here because this degree here is simply, well, this is L at the power let's say F. So what I'm dividing by, oh, sorry, right, I was going too fast. You're perfectly right. Yeah, I was thinking of P1 times P1. Okay. Sorry about that. Thank you. But of course, in general, you have a similar description. And again, in general, you already need both of the degrees to go to infinity to get the thing as free as you want. Okay, so now I would like to start with the next example. So from now on, I will, in the arithmetic case, look only at the case where, or almost, at the case where the line bundle I'm using is not a canonical one. Anyway, so I think it should be something like A5. So the plane blown up over Q. So I'm quite glad that up to now I did not have to explain to any authorities why I had some things about the plane blown up in my files on my computer, because it could take some time. Anyway, so what I'm looking at, well, this is the blowing up, let's say, of the point with coordinate 0, 0, 1 in P2. So I shall denote this point by P naught. And, well, I can describe it. Well, it is possible to describe it in P2 times P1. Well, it's over Q. And it's, well, let's take some coordinates x, y, t, u, v. And it's given by the equation well, Vx is equal to y times u. And here I have a map which I denote by pi, which is in fact the restriction of the first projection, and which goes to P2 of Q. And as you know, well, if I denote by E the inverse image of P naught, then this is isomorphic to P1 of Q through the second projection. And if I take the open subset U, which is V minus E, then this is isomorphic through P to the projective plane minus the point P naught. Okay? Well, since this surface is embedded in P2 cross P1, we get again a two parameters family of embeddings in the projective space, and therefore a two parameters family, sorry, of heights. And I should say that in fact we get everything, because the Picard group of V, I can describe it as Z times lambda plus direct sum Z of E, where lambda is the inverse image by pi of some line L, where L is a line in P2 which does not contain P naught. And I can describe both the effective cones and the ample cone. So Cf of V. So by definition, this is, let's say, the closure in the Picard group of V tensorized by R of the cone generated by the classes of effective divisors. And in that particular case, you can compute it quite easily, and it's given as, well, it's generated as a cone by the class of E and the class of lambda minus E. So lambda minus E corresponds to the strict lifting of a line going through P0. And the cone, the ample cone of V is given as the cone generated by the class of lambda plus the class of lambda minus E. And in fact, lambda and lambda minus C correspond to two morphisms, namely lambda corresponds to the morphism pi, and lambda minus E corresponds to the morphism given by the second projection to P1. For the first one, yes. For the second one, no. Sorry? No. On the first one isn't either. Yeah. So here I wrote strictly positive to mean that I'm taking only strictly positive coefficients. Right. So when I wrote this means with both coefficients strictly positive. Okay? Anyway, I'm not using it that much, so it doesn't matter. So again, we can easily describe the heights corresponding to some combination of lambda and lambda minus E. So the height of some points which I describe as PQ again is, well, the height for P2 of P at the power M times the height for P1 of Q at the power N. So nothing new there. And I can also look at the corresponding height zeta function with two parameters. So let me write the two parameters slightly differently than before. The point is that, oh sorry, it's V. The point is that I can look at the two parameters in fact as an element of the Picard group tensorized by C, which is a natural way to do it. So zeta of S times lambda plus T times lambda minus E. So I see this as belonging to some upon subset of the Picard group tensorized over Z by C. This is the sum over all points, well, over all points P and Q belonging to V of Q of 1 over HP2 of P power S times HP1 of Q at the power T. But then I'm going to use the geometry of my surface, namely I have some kind of exceptional divisor which is E. So I shall decompose this height zeta function into two terms corresponding to the points which belong to E and the one which belongs to U. So I simply write it does well, there I take the sum for P in E of Q, and here the sum for P in U of Q. Well, the component of this sum corresponding to E is quite easy to understand because, in fact, E, as I said, is isomorphic to P1. And if you look at the height is simply, up to a small transformation, the height of P1. So more precisely, I get that zeta of E, well, let's say of Rs. So the component, well, the point Q, I can take Q to be a constant equal to 1, 0, so to be of height 1, and therefore I get exactly the height zeta function for P1 of R. On this, I know the behavior, so except I'm completely wrong about the terms. So, oh, sorry, I mixed the things. So, I should be more careful. So, on E, okay. Oh, I mixed the things, sorry. On E, we have that the points are P not Q, where Q is belonging to P1. So what I wrote is completely wrong. This is zeta of P1 of S. Yes? Oh, good question. Thank you very much for this brilliant remark. So I should write this. It's different of my notes, so I have to be careful. Thank you. Anyway, I have to take the second parameter. And this is, as I said, so something like 2 times zeta q of S minus 1 over zeta q of S plus some constant. Okay, so this finish the computation for zeta E. So it remains to compute zeta of U. So this is slightly more difficult, but the spirit to compute it is to look at the fibers of the second projection. So more precisely, so S and T, I write it as the sum for Q belonging to P1 of Q of zeta of Ux of S and T, where Ux is a fiber of the second projection which is also, in fact, intersected with U, and which is isomorphic to an affine line. So I see it, in fact, in the projective. And what is the height for a point on such a fiber? So if everything is over Q, well, if X has coordinates, or Q has coordinates U and V, well, the fiber is the point of the form, well, I shall use U and V in Z with GCD of U and V is equal to 1. the fibers is described as a set of Q minus B times V sorry. No, that's not correct. A, V, B, where A, B is in the projective line, and also I want A to be different from 0. Well, of course I forgot, but there is also U, V. So in other words, I'm parameterizing the elements of UQ by these elements A, B. So this is a parameterization of each fiber. So now what is the height of that? Well, so the height I get is, well, the sum for UQ, so zeta of UQ of S and T is given by the sum for A and B in P1, well, let's say A and B in Z2 with I different from 0 and AB coprime. I hope I didn't forget any condition. Of what? Well, I have 1 over the maximum of U and V at the power, so this is the second point. So T times 1 over the maximum of absolute value of A times maximum of the absolute value of U, absolute value of V, absolute value of B. At the power S. Okay, so you do the computation, you can compute everything completely explicitly. And after these computations, which I shall spare you, you get that so after some computations, well, you get that the main term of this zeta function will be given by some formula, which is zeta of U of ST is something like 4 times zeta of Q of S minus 1 times zeta of Q of S plus T minus 2 divided by zeta of Q of S sum zeta of Q of S plus T minus 1 plus some error term or function RST which converges on is holomorphic for what did I wrote on my notes? R plus S bigger than 2 or R bigger than 1 or and no or. Okay. Okay, so let me conclude all this. So you see, where do I get some pole here? I get sample here for S plus T. S plus T equals to 3. And here for S equals to 2. So I can draw something which is in the Picard group of V tensorized by C, or rather by R, because I want to draw on the blackboard. So I have two domains of convergence. So let me start with the one for zeta of E. So zeta of E, oh, there is something wrong there. Oh, it's T, sorry again. It's terrible. I changed my notation from my notes on now. So, sorry, here it was some T. So here it converges for T bigger than 2. So if I write so let's say T and S. So, no, it should be, oops, that's a mess. Well, let's try S and T. So this one converges for T bigger than 2. So it's something here. And well, here I say that S has to be bigger than 2. So it's something around here. And S plus T has to be bigger than 3. So S plus T bigger than 3, something which I don't get, which goes through this, something. So some domain like that. So this is for zeta of U, and this is for where did I put the choke? This is for zeta on the exceptional line. So what do I see from this picture? From this picture, I see that in that domain, here, I have that zeta of U is converging, and zeta E is not converging. So what does it mean that zeta of U is converging and zeta of E is not converging? This means that there are many more points in E than there are in U. So in the green area, there are more points in the strong sense on E than on U. So let me switch back to white chalk. And in particular, where is omega v minus 1? Where omega v minus 1 it is equal to 3 lambda minus E, that is 2 times lambda plus lambda minus E. So where is it on my picture? Well, it's here. And where is the effective cone? Well, I said that the effective cone was generated by E and, where is E? So E is somewhere here. And by lambda minus E, which is here. So the effective cone is that one. So zeta of u converges for over omega v minus 1 plus the effective cone of v plus, well, I should say, take the interiors this time, plus I times the picker group of v tensorize. So the imaginary part doesn't count into this. Well, except that if I was looking at zeta v, well, zeta v converges in this much smaller area. In the term of distribution, this means that, and I shall finish on that, if I take the measure on v of height less than b, then these converge for omega v minus 1 to a measure supported by the adelic points of the exceptional line. But if I look at the distribution for points in U for the anticanonical line model, so mu of U h less than b for omega v minus 1 converges to a nice continuous measure. So there is equidistribution. But you have to restrict yourself to the points in U. So tomorrow I will explain what is the geometric counterpart of this accumulating phenomena. So I